So in the previous video, we went through the simple formula for the Taylor approximation where we have a linear term only. Later on, we realized that our answer wasn't that accurate after all, and we decided to include the second term and, if necessary, the third and fourth term. So the more accuracy we want, we need to go down the derivatives further. So ultimately, so we have this, we went with the following formula. So f of x is approximately equal to f of a. So if x is nearby a, so as x is closer and closer to a, this formula will work better and better. So we have f of x is approximately equal to f of a plus x minus a f prime of a plus x minus a squared f double prime of a, all divided by 2, plus, let's do one more term maybe, x cubed f triple prime of a, all divided by 6, and so on. So if you put 3 dots and if you go all the way up infinity, obviously that will be exactly equal to. But in our case, because for practical purposes, we are going to write a code, for instance, or use a software like Excel to do the calculations. So ultimately, we need to stop after a certain number of steps, depending on how many decimal places of accuracy one needs, right? As x gets closer to a, the approximation is better. The approximation is better. All right, so just let me go ahead and give you yet another example. And the function that I have, the function of interest that I have is sine of x. So what does the Taylor approximation does? So I'm going to approximate the value of sine of x, because it's hard to calculate it, near the point, say x is equal to 0. So let's just go ahead and draw the this function. So what we have is, obviously the sine function always ranges between -1 and 1. So this is a +1 here, -1 here, the x-axis and the y-axis. And remember earlier we discussed the whole function. So maybe this is 2 pi and this is -2 pi. We have pi and pi minus pi. And so if you guys remember it, so it was taking the value of 0, 0 here. For every integer multiple of pi, the value of sine of x is 0. Pi over 2 is 1. 3 pi over 2 is -1. And similarly, minus pi over 2 is a -1. And then -3 pi over 2 is a +1. And as a result, the sine function looks like this. There you go. Something like, and it keeps going on and on like this. It's always oscillating between -1 and 1. So when we use the very first approximation, the first term is a constant term, and indeed if you were to evaluate it at the point 0, f of 0 will come out as sine of 0, which is obviously 0. All right, so the next term here will be, so we need to calculate also f prime of 0. So because f prime of a here. So the derivative of sine of x is cosine of x. So we need cosine of 0, which is just a 1. So therefore, if you were to just use the initial 2 terms, which is usually, well, this is the first term. We always need that term. And then on top of it, we use that second term. Then we would get our first order of approximation. So, oops, let's do it again. There we go. So sine of x, as a result, will be approximately, so f of 0, which is 0, plus, so because f of 0, we just calculated it to be 0, plus x minus a, x minus 0, times f prime of 0, which is just a 1. So that will be our first order of approximation. So sine of x is approximately equal to just x. So let me just go ahead and draw that, the graph of y equals x. It turns out that what it is saying is something like, well, because this is pi over 2, pi over 2 is, as I said earlier, 1.57. So sine of x will be a function which will, so y equals x, I should say, this one, will be a function which looks like this. There we go. So at the point 1.57, it will take the value of 1.57, 1.57. So this is y equals x. All right, so this is more or less an approximation. What it does is for points nearby 0, this is a rather nice approximation, as the error terms, as you can see, is not too big. So for instance, at that point, the error term sine function says this value versus the error the approximation function. So this is the size of the error term. All right, so what were to happen if I added yet another term in that approximation? What if we also included this term? Let's quickly go ahead and check what is going to happen next. So I need, for that purpose, I need the second derivative of our function. The derivative of cosine of x is minus sine of x. So as a result, f double prime of 0 would have been minus sine of 0, which is 0. Well, because it is 0, this whole term will collapse. And there will be 0, so there won't be any further action needed. So what I need is check the next term, probably, right? So there's nothing coming from that term. So next I will be checking this term. All right, for that we need the third derivative. All right, so we need the third derivative of sine of x. Remember, the first derivative of sine of x was cosine of x. The second derivative was minus sine of x, and the third derivative evaluated at 0. The third derivative will be minus cosine of x. Evaluated at 0, minus cosine of 0 is just 1. Minus cosine of 0 is just, sorry, minus 1, I should say. All right, so therefore the new approximation will end up looking like this. So maybe I can use a blue color again. So sine of x is approximately equal to, so we got a 0 from the first term, so 0 plus, we got an x from the second term, which is this one. We got yet another 0 from the third term, and now finally we are on that purple term. We should start with 1/6, multiply it by x minus a cubed, and then multiply it by f triple prime of a, which is minus 1, right? So plus 1/6, we have that minus 1, and then x minus 0 cubed. Do you guys see that? So this thing is equal to, so these two zeros, we can just get rid of them. So it is just x minus x cubed over 6. Now, when you further plot that into our picture, notice what will happen. So you can use a software like Wolfram Alpha if you want, but the function will look like this, believe it or not. So because the x cube has a negative sign in front of it, so it will look like this. Oops, like that. And then over here it will, oops, it will probably look like that. There you go. It will be a cubic function, which is, now it's even closer approximation. It's very hard to see the error term over here. Only if you go far enough from 0, you will start seeing some error term. Do you guys see that? And the same thing on the other side. Only after a while you start seeing some error terms. So the approximation gets better and better. So if we did yet another term, adding another term or 2 into our approximation, the approximation will be even more precise than it already is. So your decision of how much precision you want basically is how many further steps, how many further terms you want to include in the actual approximation. So let's just go ahead and have a look at another example, and that will be the last example related to this topic. So let me just go ahead and call it example 2. For example 2, we want to evaluate, for instance, find the value of, as approximate as possible, let's say e to the power, let's say I don't know, so let's say 0.5 or let's say 0.5, let's say. That's what I want to evaluate. So evaluate this. So where, let me remind you that where e is the Euler number, and I think in an earlier problem we looked at its value. Let me check my calculator for the exact value of that. So there's a function on the on each scientific calculator. So the exact value is 7182818. So, and then there's another 28 actually. So, but because we need to raise it to the 0.05th power, so let me just go ahead and take that power, raised to the power 0.05. The answer comes out as following. So the calculator tells me, and let's see if we can do it without a calculator, says that e to the power 0.05 is equal to, given that e itself is this, using a calculator, it gives me 1.05127, say 11. Okay, so I stopped after 7 decimal places. Let's try to find that result as well. So the function of interest as a result will be e to the power x, which is an exponential function. And we want to evaluate it at the point x equals 0.05. All right. And so for that purpose, because 0.05 is extremely close to the point 0, I'm going to take the value a equals 0. So let me just go ahead and take the first few derivatives of this function. The good news is e to the x is the only function whose derivative is itself. As a result, I keep taking further and further derivatives. It's always going to be e to the x. So finally, the approximation for e to the x as a result will be the following. So we start with, because I'm approximating at the point a equals 0, you guys, all you need is to just plug in the value 0 here in each of these. Each time it will be e to the power 0, which is just a 1. So it will boil down to the following: 1 plus, or let me do it in 2 steps maybe. So it is e to the power 0 plus x minus 0 e to the power 0 plus x minus 0 square e to the power 0 all divided by 2, and so on. Do you guys see that? So we will decide how far we want to go in this formula. Let me write actually one more term. X minus 0 cubed e times e to the 0 divided by 6, and so on. All right, so let's just go ahead with the first term, which is just a 1. So therefore, e to the x is equal to 1 plus, well, x minus 0 is just an x times e to the 0, that's just an x, plus x minus 0 square is just x squared times 1, so this is just a 1 divided by 2, so this is just x squared over 2, plus, and the next one would be x cubed times 1, x cubed all divided by 6, and so on, x cubed over. So you guys seeing where this is going? X to the 4 divided by 24, so 4 factorial, and so on. X to the 5 divided by, if you further multiply it by a 5, and so on. So you can stop wherever you want, depending on how many decimal places of accuracy. For instance, let's see how far we need to go until we get this result. So all we need is e to the power 0.05, replace wherever you see an x with a 0.05, so it is 0.05, so 0.05 here, plus 0.05 square divided by 2 plus 0.05 cubed divided by 6, that's a 5, believe it or not. Let's just make a correction there. 0.05 raised to the 4th power divided by 24, and so on. All right, so let's just use our calculator as usual. 1 plus 0.05 plus, all right, so 0.05 square, and then I will divide it by 2. 0.05, I square it, divided by 2. That term comes out as 0.11. Actually, let me write it as accurate as possible. 111.803399. Wow, wait, we have more than accurate. So I needed 7, right? So 3. Yeah, I needed to stop right here. So that's a 4. There you go. Plus, then this term. All right, so that term, is 0.05. Okay, 0.05. We are going to go ahead and cube it and then divide it by 6. So that's going, wow. So that term is extremely small. It's actually 0.000. It's already telling you that the approximation will be quite accurate, right? So 1, 2, 3, 4, 5, 6, 7. Okay, that's it. And lastly, let's try one more. So this very last term, so 0.05, let's go ahead and do that. 0.05 to the 4th power. Oh gosh, this is already extremely tiny. So it is 0.0034567. The 7th would be a 3. So 0.000000, and the last term will be a 3. So if I were to add these up, let's see what comes out of it. So I would end up having, so let's plus 0.00040208 plus 0.118803 plus 0.05 plus 1 equals, oh gosh, I think I messed up. Okay, so let's just go ahead and do that again. So the actual answer was, oh, actually I was close. Hold on. I don't think I messed up. So this is what we are trying to get, right? So all right, so let me just do it again. So obviously there's a 1.05 from the first two, then further adding 111. So I think it will become 161, right? So 1618034, and then I need to add these very tiny, very tiny terms, which is 0.0000211. Does that make sense? All I did was to add 208 with the 3 in the end. So if you add these, okay, so this answer will come as 618245. Now let's compare this with what we have. 1.05127. Wow, it's a little bit off. Okay, so let me check my calculations one more time. I think I might have messed up with the division by 2 over there. Let me quickly check. Because it's already positive, which is kind of weird. Let me do it again. Hold on. So I have E here, 2.71. Okay, and I want to raise it to the power 0.05. Yes, that one is correct. So that's the overall final answer that I want to get, right? So we decided to start from the 0.0 because 0.05 is extremely close to 0, and then keep adding terms from there, right? So yes. So this is f of x, or f of 0, I should say. This is f prime of 0, f double prime of 0, and so on. So all I need is these remaining terms. So let's check. So we have 1 plus x squared over 2. Our x is 0.05. All right. So this number came out surprisingly big. Let me double check this one. Hold on. That number was supposed to be much smaller. Okay, so I probably messed up over there. So 0.05, if I square it, further divided by 2. Okay, so I messed up that one pretty badly, actually. Okay, let me revise my notes. There you go. So this one was pretty messed up. All right, so this one was supposed to be, okay, so that's what caused all the troubles. All right, so let's quickly check. So that number came out actually as 0.00125. There you go. All right, now when I add them, so here we start 1.05. And then I continue with that 125, or you can just directly add those 5 numbers that you see on the screen. And then we have, starting from the fifth, 1, 2, 3, 4, 5. So we have a 208 there, and then finally there will be another 3 here. Do you guys see that? So 0, 0 here. So that one will be a 1. It will carry a 1, a 7, a 2, a 1, a 5, a 0, a 1. 1.0512711. The actual correct one was 1.0512711. Wow, that's it. So in just going as far as the first 4 terms, we were able to get up to 7 decimal places of accuracy. Our error term is less than 1/10 of 1 millionth. So it is extremely accurate. All right, so I hope that was a good example to summarize this whole concept. Let me actually make it smaller so you guys can see the whole example in front of you. So basically, it's up to us to decide where we want to stop when we use this Taylor approximation. You can stop after, usually it's common practice to stop over here after the first 2 terms, which in this form it would end up becoming a linear approximation. However, it's common to keep adding more and more terms if you want an even more and more accurate answer. And obviously this is an infinite sum, so it's up to you to decide where you want to stop this approximation, right? So it can go forever. For instance, in this case, we decided to go 1/3, the 4th, and stop it right here at the 5th term. And it already gave us an extremely close approximation comparing this with that. And that's it.